Welcome to Unit 15, Video 2, Reaction Quotient. By the end of this video, you should understand how a reaction quotient is different from an equilibrium constant, and you should be able to use the reaction quotient to predict whether a reaction is at equilibrium, and if not, which way it will proceed. The reaction quotient, which we abbreviate with a capital Q, is the value calculated using the equilibrium expression and current concentrations. The system may or may not be at equilibrium. We just have a set of concentrations, and we're not sure if those concentrations represent equilibrium concentrations. So we can use the reaction quotient to determine if a system is at equilibrium or in which direction it will proceed or shift to achieve equilibrium. Will it go forward or will it go backward? Or is it already at equilibrium? Consider this reaction with an equilibrium constant of 0.105 at this particular temperature. If I have this system and I measure the concentrations of reactants and products and find them to be as listed, I can ask if this system is at equilibrium, and if not, will it proceed in the forward direction or the reverse direction in order to achieve equilibrium? In order to use the reaction quotient to make this determination, first, I want to set up an equilibrium expression. For this reaction, our equilibrium expression would be KEQ is equal to the concentration of NH3 squared over the concentration of N2 times the concentration of H2 to the third. Again, we use the coefficients as our exponents in our equilibrium expression. Then I'm going to substitute the concentrations given from the above equation into the equilibrium expression. Since I'm not sure if these concentrations are equilibrium concentrations, I'm going to call this expression my Q expression. Notice it's exactly the same as my K expression. I've substituted in the values, but I'm calling it Q instead of K because I'm not sure if calculating these values will give me the equilibrium constant or not. In fact, they don't. When I input these values and calculate my Q value, I get 8.33. Now consider, if this reaction were at equilibrium, what should Q be equal to? Well, if it were at equilibrium, then Q should equal K, because our concentrations would represent the ratio that gives us the equilibrium constant. However, here we found that Q is much greater than K. So what does this mean? Well, this means that our numerator must be too large or our denominator must be too small. In other words, we have too much product and not enough reactant. So the system, in order to achieve equilibrium, will have to proceed in the reverse direction, thereby lowering the amount of product and increasing the amount of reactant in order to get Q to equal K. Summarizing this observation, we found that Q is greater than K, meaning the denominator of Q is too small and the numerator is too large. Also meaning that there's too much product and not enough reactant, and also indicating that the reaction will proceed in the reverse direction in order to reach equilibrium. On the other hand, if Q is less than K, the opposite is true. This would mean that the denominator of Q is too large and the numerator is too small, meaning there's too much reactant and not enough product. Therefore, when Q is less than K, the reaction will proceed in the forward direction in order to make more product and use up some reactant. Finally, if Q is equal to K, that means that the system is already at equilibrium and no shift will occur. Looking at this visually, here in the middle we see that Q is equal to K, therefore the system is at equilibrium. On the right, Q is greater than K, meaning there's too much product and not enough reactant. Therefore, our reaction will have to shift left in the reverse direction. On the left here, Q is less than K, meaning that there is too much reactant in the system. So the reaction will proceed to the right in order to use up that reactant and make more product. Here's a problem to consider on your own. Notice that this problem does not give you concentrations, but it does give you moles and liters. Therefore, the first step here will be to calculate concentrations for each of your reactants and products before solving for Q. Pause the video here. When you come back, I'll reveal the answers. Welcome back. Here's what you should have gotten. After solving for concentrations and plugging them into the Q expression, we found that Q is less than K. Therefore, the reaction will proceed in the forward direction in order to increase the amount of product and decrease the amount of reactant. That brings us to the end of this video. Let's review our goals. First, we looked at how the reaction quotient is different from the equilibrium constant. Q, the reaction quotient, is calculated using current conditions, where the equilibrium constant, K, is calculated using equilibrium conditions. Then we learned how to use the reaction quotient to predict whether a reaction is at equilibrium, and if not, which way it will proceed. When Q is equal to K, the system is at equilibrium. When Q is greater than K, the reaction will proceed to the left in the reverse direction in order to achieve equilibrium. When Q is less than K, the reaction will proceed to the right in order to achieve equilibrium.